I want you to picture something for a second. You just dropped well over $1 million on a state-of-the-art hypercar. We are talking a full carbon fiber monocoque chassis, a V12 engine that sounds like a literal fighter jet taking off.
Oh yeah, just a total engineering marvel.
Exactly, the absolute pinnacle of aerodynamic engineering. So you strap into the seat, you grip this Alcantara steering wheel, you pull out of the dealership, and you drive it exclusively in first gear.
Oh, man.
Right. Just in first gear over a series of speed bumps in a Walmart parking lot.
Well, okay, the visual of that is actually stressing me out a little bit. The suspension alone would be completely ruined.
It is entirely absurd. You possess all this incredible world-class potential, and it is just completely wasted because your driving strategy is, well, it's fundamentally incompatible with the equipment.
Right.
But here is the thing for you listening today. Mm-hmm. This exact scenario plays out in manufacturing facilities every single day.
It really does. All the time.
Yeah, machine shops will invest heavily in these highly advanced carbide cutting tools only to run them using outdated, mismatched, or frankly, just abusive strategies. So welcome to this deep dive.
Gotta be here.
Today, we are exploring a really fascinating text on optimizing carbide performance with ISCAR and CAM strategy. We're focusing heavily on a philosophy they call the MAXOUT concept.
Which is such a crucial topic right now.
It really is. Our mission today is to figure out how the physical tools, the software driving them, and the digital planning beforehand all intersect to drastically lower the cost per component.
And, this is incredibly relevant because the pressure in modern manufacturing is just relentless.
Oh, I can imagine.
Yeah, shops aren't just trying to make parts anymore. They are trying to shave milliseconds off cycle times while simultaneously extending the life of their tools.
Right.
If you are just throwing expensive cutting tools at a solid block of titanium without a holistic system, you are literally just burning money.
Okay, let's unpack this core physical component first, because everything here basically revolves around carbide.
It does. It's the foundation.
Right. In metalworking, carbide is essentially a miracle material. The text notes it is the backbone of milling, drilling, turning, grooving, threading, you name it.
Pretty much every major operation, yeah.
But for those who might not spend their days, standing in front of a CNC machine, we are talking about a material engineered for extreme hardness and serious heat resistance.
Absolutely.
Like you can maintain a razor-sharp cutting edge at temperatures that would literally melt traditional steel tools. But I have a bone to pick with this text.
Oh, okay, let's hear it.
Well, if this material is supposedly so incredibly tough, why does the source material spend so much time talking about it chipping, vibrating, or just catastrophically exploding inside the machine?
That's a fair question.
Honestly, it sounds like someone is just buying a cheap, defective product and trying to blame the strategy instead.
See, that is the most common trap operators fall into. When a tool snaps, the immediate reaction is to blame the tool manufacturer.
Naturally, yeah.
But you have to distinguish between hardness and toughness. They aren't the same thing. Carbide is incredibly hard, which allows it to shear away tough metals like Inconel or hardened steel.
Right.
But because it is so hard, it is also inherently brittle. Think of a glass window. It is hard enough to resist scratches from most everyday objects, but if you strike it with a hammer...
it just shatters.
Exactly. It shatters because it cannot flex. It has no elasticity.
Ah, okay. So it really just can't absorb shock.
Correct. Failure is almost never a defect in the carbide itself. It is a failure of the conditions that are applied to it.
That makes a lot of sense.
The text points out that catastrophic failure usually comes from incorrect feeds and speeds, or excessive radial engagement, which basically just means the tool is biting too deeply into the side of the metal at one time.
So it really is the hypercar over the speed bump.
It is exactly that. Let's look at the tooling mentioned in the text. You have solid carbide end mills, which are ground from a single cylindrical blank of carbide.
Okay.
And then you have indexable milling cutters, which use a tough steel cutter body with small, replaceable carbide inserts bolted onto it.
Right, I've seen those.
So if you take a high-efficiency indexable cutter that's designed for light, fast cuts, and you bury it deep into a block of steel using a traditional heavy tool path, that carbide insert will shatter instantly.
Because it's too much shock.
Exactly. You are subjecting a rigid, brittle material to a massive load it just wasn't designed to support.
Or, the text also mentions drills with advanced coolant through capabilities. These are drills with tiny, like microscopic holes running all the way through the tool to blast high-pressure coolant directly at the cutting tip.
Which is a brilliant piece of engineering, truly.
But if the programming strategy doesn't allow the chips to evacuate, like if you let the metal shavings cack tightly into the hole you are drilling, that advanced coolant system doesn't mean a thing.
No, it doesn't.
The chips will bind, the heat will spike, and that expensive drill will just snap off right inside the part.
And getting a broken carbide drill out of a part is a nightmare. So buying the best physical object is essentially meaningless if the ecosystem surrounding it is flawed.
Which is a huge takeaway for you listening, honestly, regardless of your industry. Buying top-tier enterprise software or, hiring the most expensive consultant, it means nothing if your internal processes actively fight against them.
Precisely. You have to set the tool up to win.
You really do. And in the context of machining, setting the tool up to win requires looking critically at the mechanism driving it.
Which transitions us from the physical metal to the digital brain. CAM software.
Right. Computer-aided manufacturing. And I'll admit, before reading this, I viewed CAM software as kind of a glorified map maker.
A lot of people do.
You load in a 3D CAD model of the part you want, and the CAM software just draws the lines for the machine to follow, like a GPS for the cutting tool.
Right, but that is a very outdated way of looking at it. Modern CAM software is a highly advanced process control engine.
Okay.
It doesn't just draw a path, it dictates the physics of the cutting event. Literally millisecond by millisecond.
So it seems closer to like the traction control and stability management system on that hypercar we talked about.
That's a perfect analogy.
It is constantly monitoring and adjusting the variables to keep the car on the track. The text outlines how CAM dictates the radial and axial depth of the cut, the ramping strategy to enter the metal, the lead-in and lead-out arcs.
Yeah, it's micromanaging everything.
It's compensating for chip thinning, rounding corners to manage internal stress. It's wild.
What's fascinating here is that internal stress, because that is where CAM really proves its worth. To understand why a cutting strategy fails, you have to look at load spikes.
Okay, break that down for me.
Sure. When a cutting tool moves in a straight line along a straight wall, the cutting forces are stable. The engagement angle is constant. But imagine that tool is clearing out a square pocket and it suddenly drives straight into a sharp 90-degree internal corner.
Oh, the geometry completely changes in a fraction of a second.
Drastically. Moving down a straight wall, maybe 20% of the tool's diameter is engaged in the metal. The moment it hits that 90-degree corner, the tool is suddenly wrapped in metal on two sides.
Right.
The engagement instantly spikes to 50% or more.
Which means the torque on the machine's spindle basically doubles, and the physical pressure on that brittle carbide edge skyrockets instantly.
Yes, and that sudden violent shock is what chips the cutting edge or completely snaps the tool.
Yikes.
So an advanced CAM system prevents this mechanically. It will never allow the tool to drive directly into a sharp corner.
What does it do instead?
It alters the tool path. It uses smooth, sweeping arcs, corner rounding, or these morphing spiral patterns. It maintains a constant engagement angle.
So the physical force on the carbide remains perfectly stable.
Exactly. Throughout the entire cut, no matter the complex shape of the part.
That's amazing. By controlling the geometry of the path, you are smoothing out the physical forces acting on the tool. That makes total sense.
It's a game changer.
And this constant engagement capability is what unlocks the next major concept in the text. This completely changes the rules of machining. High-efficiency milling.
Yes. High-efficiency milling, or HEM. You'll also hear it called dynamic milling or adaptive clearing, depending on, which CAM developer you ask.
Right.
But this is the perfect illustration of matching ISCAR's advanced tooling with the exact correct software strategy.
Here's where it gets really interesting, because it flies in the face of traditional machining logic.
It really does.
If I picture someone machining a massive block of steel, I picture them taking these heavy, aggressive, horizontal cuts, just burying the side of the tool deep into the material to hog it out as fast as possible.
That is the legacy approach, for sure. But think about the physics of that heavy radial cut. You are burying the tool horizontally, but usually only cutting a shallow amount vertically.
Okay.
That means all the heat, all the friction, and all the wear is concentrated on the very bottom quarter inch of the cutting tool.
Oh, I see.
You are destroying a tiny fraction of the carbide while the rest of the flute length does absolutely nothing.
Which brings us to how high-efficiency milling flips that upside down. Instead of a heavy, deep horizontal bite, you take an incredibly light radial cut, just skimming the side of of the tool against the metal.
Exactly.
But you pair that with a massive axial cut, you drop the tool all the way down and use the entire vertical length of the cutting edge.
The brilliance of this is heat dissipation and wear distribution.
Right.
By engaging the entire flute length of a solid carbide end mill, you are spreading the cutting forces over a much larger surface area. The localized heat drops significantly.
That makes perfect sense.
And because that horizontal bite is so incredibly thin, the sudden shock to the tool we talked about earlier is basically minimized.
But the text throws a massive warning flag right here regarding the physical chip of metal being peeled away.
Oh, the Goldilocks chip. Yes.
Yeah, if you are taking these microscopic radial cuts, the chip thickness changes. And apparently, if that chip gets too thin, you are setting yourself up for a complete disaster.
A very expensive disaster, particularly in aerospace materials or stainless steels. This all comes down to the mechanics of cutting versus rubbing.
Walk me through the physics of that, because I would assume a thinner cut is a safer cut. Less pressure on the tool, right?
It seems logical, sure. But cutting metal isn't like slicing butter. It requires a specific amount of force to actually shear the material.
Okay.
If your chip thickness falls below a certain threshold, the cutting edge of the carbide can't actually bite into the metal. Instead of shearing a chip away, the tool just skips and rubs aggressively against the surface of the workpiece.
And rubbing creates friction, which creates heat.
Massive amounts of heat. And in certain materials, like austenitic stainless steel or titanium alloys, that localized heat and pressure literally alter the molecular grain structure of the metal ahead of the tool.
Wow.
It is a phenomenon called work hardening.
So by trying to be gentle and taking too thin of a cut, you are actually forging a hardened, impenetrable crust on the part right before you try to cut it again.
Yes, you are actively making your job harder. The next time the cutting edge comes around, it hits that hardened crust and wears out almost immediately.
Okay, so you absolutely cannot let the chip get too thin. But the geometry of a light radial cut naturally creates a thinner chip, doesn't it?
Yeah.
Because you are only shaving the very edge of a circle.
That is the concept of radial chip thinning. If you advance a circular cutting tool forward, the thickest part of the metal chip is at the direct center line of the tool.
Right.
But as you move out toward the extreme edge of the circle, which is where high-efficiency milling operates, the physical thickness of that chip tapers off geometrically.
So how do you fight that? I mean, if the geometry forces the chip to be too thin and a thin chip causes work hardening, how does high-efficiency milling actually work?
This is where the CAM software intervenes. Because the CAM system knows the exact geometry of the tool and the exact width of the cut, it dynamically recalculates the feed rate.
Oh, wow.
Yeah, to maintain the proper chip thickness at the very edge of the tool, the software commands the machine to drive the tool forward significantly faster. It speeds up the linear motion to compensate for the geometric thinning.
That is incredible. The software is constantly manipulating the speed of the machine to keep the cutting physics in a perfect state of equilibrium.
It's beautiful, honestly.
But this brings up a huge logistical problem. If you are the person staring at the computer screen trying to program this part, how do you determine the baseline numbers?
That's the challenge.
You can't just guess the starting feed rates or the exact carbide grade for material you've never machined before. I mean, trial and error with titanium and million-dollar machines is a pretty good way to bankrupt a shop.
You absolutely cannot guess, and that is why the text shifts from the CAM software to the concept of the digital twin.
Okay, let's talk about that.
You have to build a mathematically perfect simulation of the process before you load a single piece of raw material into the physical machine. This starts with ISCAR's NEO-ITA platform.
Their online tooling advisor.
Yes, is fundamentally a process planning engine. You input the specific parameters of your job, like the exact alloy you are cutting, the type of operation, whether it is facing, pocketing, or drilling, the capabilities of your machine, and your production goals.
And it takes all those variables and just outputs the exact ISCAR tool family you need.
Exactly.
The specific insert geometry, the carbide grade designed for that metal, and the mathematically proven starting speeds, feeds, and depths of cut. It's like a cheat code.
It really is. It provides the CAM programmer with a verified, data-driven foundation. You aren't relying on tribal knowledge or, thumbing through an outdated paper catalog.
Right. Having the perfect mathematical cutting data is obviously crucial. But the text spends an enormous amount of time discussing the digital mapping of tool assemblies.
Yes, very important.
And I have to admit, I struggle to see why this is so critical. If NEO-ITA gives me the perfect speed and feed, and my CAM software creates a perfect high-efficiency tool path, Why does it matter if my 3D model of the metal holder gripping the tool is slightly off?
If we connect this to the bigger picture, it's because the software's math assumes a perfectly rigid system, and the physical world is anything but.
Okay.
Let's look at the physics of rigidity.
Yeah.
Imagine holding a pencil. If you grip it right near the tip and press down on a piece of paper, it is incredibly stable. You can apply a lot of force.
Right, makes sense.
Now hold that exact same pencil by the eraser and try to apply that same force to the tip.
The pencil bows and snaps.
That is the concept of stick out in machining. A cutting tool is never just a piece of carbide. It is a massive assembly. You have the machine spindle, a retention knob, the tool holder itself, maybe an extension or a collet chuck, and finally the cutting tool at the very end. Every single connection point and every millimeter of length added to that assembly acts as a lever arm. It amplifies the cutting forces.
Meaning the further the cutting edge is from the spindle, the less rigid the setup becomes.
Exactly. And lack of rigidity causes chatter, microscopic vibrations. Because we already established that carbide is exceptionally hard but brittle, that high-frequency vibration will literally microchip the cutting edge into dust, even if your mathematical speeds and feeds from Neoida are flawless.
Wow. Wait, so even if my mathematical cutting data is perfect, if I don't digitally model the holder exactly right in the software, it can ruin the physical part.
Absolutely. So the digital tool assembly isn't just about drawing a pretty picture in the software. It is about simulating the physical constraints. It is about collision detection and gauge length. If you don't use accurate online tool assemblies to digitally construct the exact holder and cutter combination, your CAM simulation is completely blind. The software might think the tool holder is narrower than it actually is in reality.
Which means the simulation shows a safe cut, but on the shop floor, the actual physical holder smashes into the side of the part.
A catastrophic machine crash. This is why a precise digital twin is non-negotiable. You have to verify the reach, the clearance, and the rigidity digitally.
But even if you achieve absolute perfection in the digital realm, perfect math, perfect tool path, perfect digital assembly, that digital twin still has to survive contact with reality.
And reality on a shop floor is completely unforgiving.
Yeah.
The text makes it very clear that all this digital optimization cannot overcome a fundamentally flawed physical setup.
So let's break down the physical showstoppers they identify. The first one is runout.
Runout is a killer. It occurs when the cutting tool isn't spinning perfectly true on its central axis.
Think of a wobbly tire on your car.
Great example.
Yeah, if the wheel is slightly bent, the tire doesn't roll smoothly.
Right.
It hops and drags, wearing out one specific patch of the rubber unevenly.
Exactly the same principle here. If a 4-flute end mill has even 1/1000th of an inch of runout, one of those 4 carbide flutes is taking a massive heavy cut, while the other 3 are barely touching the metal.
Oh, man.
You destroy that single cutting edge rapidly, which throws the tool further out of balance, leading to total failure.
So a pristine tool holder is required.
Right.
What about work holding?
We talked about rigidity in the tool assembly, but the workpiece itself has to be equally rigid.
Right.
If the block of metal you are cutting isn't clamped down securely, the part itself will act like a tuning fork. It will vibrate against the cutter, and again, vibration shatters carbide.
The last major physical barrier mentioned is chip evacuation.
We touched on this with the drills earlier. When you are performing high-efficiency milling, you are generating thousands of chips per minute. If you do not have adequate coolant pressure or a strong air blast to physically clear those chips out of the cutting zone, the tool will just trap them.
And recutting chips is basically a death sentence for a tool, right?
Oh, absolutely. You are asking the carbide to shear through metal that has already been sheared, work-hardened, and broken. It causes a massive spike in heat and load, and the tool will snap almost instantly.
Okay, so what does this all mean? This entire journey, from the chemical makeup of the carbide to the geometry of the cam tool path to the digital twin to the physical clamping of the part, it all brings us to the ultimate objective. ISCAR calls this the MAXOUT strategy.
Yes, the MAXOUT concept.
But I think there's a huge misconception here. If you ask most people what the goal of optimizing a CNC machine is, they would probably say to run the machine as fast as humanly possible.
That is a huge trap. This raises an important question about what the actual goal of manufacturing really is. The text explicitly states that the objective of the MAXOUT strategy is not simply increasing cutting speed. The true goal is reducing the overall cost per component.
which requires a much wider perspective than just looking at feed rates.
Pushing a machine to its absolute maximum speed might shave a few seconds off the cycle time of a single part. But if that aggressive speed introduces instability, causes chatter, and breaks a $200 carbide tool twice a shift, your cost per part actually skyrockets.
Yeah, that makes sense.
You have increased your tooling costs, and more importantly, you have increased machine downtime while the operator has to stop and swap out broken tools.
So the MAXOUT philosophy is really about total process reliability. You integrate the data from NeoIDA, you utilize the precise digital tool assemblies, and you program high-efficiency CAM strategies not just to go fast, but to create a highly predictable, stable environment.
Predictability extends tool life. It reduces scrap parts. It minimizes the time the spindle is sitting idle. By harmonizing the physical tool, the software, and the setup, you maximize the return on the carbide you purchased. That is how you drive the cost per component down.
It all comes back to not driving the hypercar over speed bumps. To recap for you listening, the immense capability of modern carbide tooling cannot be unlocked by brute force. It requires a delicate, interconnected ecosystem.
Very much so.
You need smart CAM strategies, utilizing light radial cuts to manage heat and prevent load spikes. You need exact digital planning, using resources like the NeoIDA to establish the correct physics beforehand. You must construct flawless digital tool assemblies so your software simulation accurately reflects reality and prevents chatter. And all of that digital perfection must rest on a foundation of a rack-solid, physically rigid setup with zero runout and excellent chip evacuation.
Every single variable relies on the others. You really cannot ignore one without compromising the entire system.
But I want to leave you with a final thought to ponder, something that builds on this trajectory of digital integration.
Okay.
Right now, as the text outlines, we use digital tool assemblies and CAM simulations to perfectly predict and plan the cutting forces before the operation begins. It is entirely preemptive. But as artificial intelligence and sensor technology advance, how long will it be before the machine tools themselves become active participants?
Oh, that's an interesting thought.
Imagine a CNC spindle equipped with sensors that can physically feel the chip thickness changing in real time due to tool wear or a hard spot in the metal. What happens when the machine uses AI to dynamically overwrite the CAM strategy on the fly, adjusting its own feed rates millisecond by millisecond to save the carbide tool without a human ever touching a dial?
The digital twin evolves from a planning tool into a real-time autonomous partner. That's wild to think about.
The systems are only getting smarter, and the ceiling for efficiency is only getting higher. Thank you for joining us on this deep dive. Keep examining the systems you rely on, make sure your strategies match your equipment, and always look for the hidden potential in your own work. Until next time.